The problem is from GATE 2016, question number 11. The problem given is, let V be the set of all solutions of the equation y double dash plus ay dash plus by equal to 0, satisfying y of 0 equal to y of 1, where a and b are positive real numbers. Then dimension of V is equal to dash. So it is given that the second order differential equation y double dash plus ay dash plus by equal to 0, and given conditions are y of 0 equal to y of 1. Then it is asked that dimension of V is equal to dash, where V is the set of all solutions of this differential equation. To solve this problem, one should know a little bit of differential equation knowledge. So I will explain how to solve this problem. So firstly, let us see the NPTEL reference to solve this problem. So the one NPTEL reference from linear algebra is module 3 lecture 2 lecture number 12 with the title dimension of a vector space by Dr. K.C. Sivakumar. He is from Department of Mathematics, IIT Madras. You can watch that. You can watch this reference video using this YouTube link. And for the knowledge of differential equation, I would like to refer another NPTEL video, that is lecture 9 with the title Introduction to Second Order ODEs from the topic Differential Equations for Engineers by Professor Srinivasa Rao Manam. He is from Department of Mathematics, IIT Madras. Even you can watch this differential equation reference video using this YouTube link. So now coming to the solution. It is given that y double dash plus ay dash plus y equal to 0, where a comma b are positive real numbers. And it is given that V is the set of all solutions of this differential equation. So firstly, let me explain the solutions of this differential equation. Sorry, here it is by. So to solve this problem, we have to consider the auxiliary equation. This is a method of solving differential equations. Auxiliary equation is given by m square plus am plus b equal to 0. And we can see the solution of this equation is nothing but minus a plus or minus square root of a square minus 4b divided by 2. And here, since it is given here that a and b are real numbers, arbitrary real numbers, so one can consider in such a way that this term a square minus 4b equal to 0. In that case, we get the roots of this equation as same and repeated. But whenever we consider a and b in such a way that a square minus 4b is not equal to 0, then we get two different. So we consider two cases here. Case 1. Case 1 is that if a square minus 4b is non-zero, then we get, and let me assume a is the first solution of this equation 1. So that is minus a plus square root of a square minus 4b divided by 2, and b is the another root minus a minus square root of a square minus 4b divided by 2. Then we get, then the solutions of these differential equations are nothing but solutions of the given differential equation are nothing but e power of a x and e power of bx, and are in total with the linear combination of these two solutions are c1 e to the power of ax plus c2 e to the power of bx. Since the given differential equation is homogeneous, so whenever we have a solution of that differential equation, the multiples of the differential equation is also a solution, and hence c1 e to the power of ax is also solution. And whenever we have solutions, linearly independent solutions, then the sum of those two linearly independent the sum of those two linearly independent solutions is also again a solution, as the differential equation is homogeneous, and hence the solution of this differential equation are of the form c1 e to the power of ax plus c2 e to the power of bx, where a and b are these two real numbers. But it is given that, so y of x are nothing but c1 e to the power of ax plus c2 e to the power of bx is the solution. Is the solution of the given differential equation. But it is given that y of 0 equal to y of 1. That implies we have c1 e c1 plus c2 is equal to c1 e power of a plus c2 e to the power of b. From this we can see 1 minus e to the power of a into c1 equal to e to the power of b minus 1 into c2. And from this we can see c1 in terms of c2. Yes, c2 times e to the power of b minus 1 divided by 1 minus e to the power of a. And from this we can rewrite the solutions of the differential equation as c1 e to the power of, okay, in place of c1 I am just writing the term we have derived, that is c2 e to the power of b minus 1 divided by 1 minus e to the power of a into e to the power of ax plus c2 e to the power of bx. And from this y of x is nothing but c2 times e to the power of b minus 1 divided by 1 minus e to the power of a times e to the power of ax plus e to the power of bx. So are the solutions of the given differential equation. So the solution space. So the solution space as given as V is generated by the vector e to the power of b minus 1 divided by 1 minus e to the power of a times e to the power of ax plus e to the power of bx, where a is minus a plus square root of a square minus 4b divided by 2, and b is minus a minus square root of a square minus 4b divided by 2. This is one case. So whenever we have the condition that a square minus 4b is non-zero, we have the dimension of v is 1. And we have another case. Yes, case 2, if a square minus 4b equal to 0, then we have, from the auxiliary equation, we have we can see when this term is 0, the only solutions of this equation are nothing but minus a divided by 2 repeated twice, and hence then by the auxiliary equation we can we have m equal to minus a divided by 2, hence y of x is c1 plus c2x e to the power of ax, or let me write cx, as we have already used the term a and b, where c is minus a divided by 2, or the solution are the solutions of the given differential equation. But it is given that y of 0 equal to y of 1. The solutions of this differential equation, as this term, this is by the given differential second order homogeneous differential equation. So one should have that knowledge, then only we can see how it is. So by the given condition we have y of 0 equal to y of 1, that is c1 equal to c1 plus c2 e to the power of c. From this we can see 1 minus e to the power of c times c1 equal to c2 e to the power of c. And from this we can observe that c1 in terms of c2 as c1 equal to c2 times e to the power of c divided by 1 minus e to the power of c. So from this we can say, so y of x equal to c1 as c2 e to the power of c divided by 1 minus e to the power of c times, sorry, okay, this is c1, okay, plus c2x times e to the power of cx. And from this we can see c2 times e to the power of c divided by 1 minus e to the power of c plus x times e to the power of cx are the solutions of the given differential equation. And hence the solution space V is generated by the vector e to the power of c divided by 1 minus e to the power of c plus x times e to the power of cx, where c is minus a divided by 2. This is in the case when a square minus 4b equal to 0, and in the case when a square minus 4b is not 0, we have derived that the solution space is generated by this vector. And in both the cases we can see the solution space is generated by a single vector. Here in the first case generated by this vector, and in the second case it is generated by this vector, and hence we can say dimension of V is 1. Hence the answer is 1. This is due to mainly this condition. If we have some other condition in place of this, we can get the dimension of V as something else. But the maximum dimension of V should be 2 only. Yes, it is second order differential equation. So but in this case, if y of 0 equal to y of n, y of 1, then the dimension of V is 1.